So welcome everyone to the AI seminar, a weekly seminar series that always has wonderful speakers on Fridays at noon. I've been fortunate to have many wonderful students over the decades, and one of the best is Roberto Vega, who's going to give our talk today. I've noticed it's his fascinating master's thesis work on batch effects and some really nice results he's done as part of his PhD work, including this paper, which appeared recently in AI Stats. This work actually began more than a year ago and involves one of our colleagues, Pune Gurki, who was on the flight that didn't make it back from Iran. So that's why I just mentioned that we still miss her. And I'm glad that she was actually part of this. She could contribute to this, and it's being honored here. Anyway, having said that, I'll let Roberto take over. Looking forward to his presentation. Thank you.
Here I am. Perfect. So just to confirm, you are able to see my slides now, right?
Yeah, looks good.
Okay, perfect. So then let's start. The title of this talk is Probabilistic Labels for Classification Tasks in Medical Images. And as was mentioned, this is like the presentation for this paper. Sample efficient learning of image-based diagnostic classifiers using probabilistic labels that was presented at AI Stats a few months ago, and it includes the very important work from Pune, who Rod just mentioned. She didn't make it back in the flight from Iran. So this work includes very important contributions of her. So let me start with a summary. Let me start with the ending. So what is the main task that we are trying to do? So imagine that we have a medical image. And this is an ultrasound image of the hip. And then we want to create a classifier. And we want that classifier to say the probability of being healthy is 96%, and the probability of having a disease is only 4%. So we want an automatic diagnostic classifier. And we did this classifier. I mean, we created 3 classifiers for 3 independent tasks. One was with images with hip dysplasia, one with images of fatty liver, and one with images of glaucoma. And there are 2 things that we care about in here. The first one is we want our classifier to be accurate. And by that, we mean that if the ground truth is that a physician said this image belongs to a healthy person, then we want our classifier to say that the probability of being healthy is more than 50%. And the second one, very important in tasks, in medical tasks, is calibration. And by that, we mean that if we take 100 cases where our classifier predicted that the probability of being healthy was 70%, then we want 70 of those cases to be actually healthy. So, but by this we mean that we want the outputs of the classifier to be actual probabilities. And this is not the case in many of the traditional neural networks. And I am going to go into more detail of this. The main result, or the main message, is that the methodology that I am going to present here works. So in the 3 cases, whenever we apply our method, that it is in this case represented by the red graph, we get a higher or equal accuracy than traditional methods. So that is the main takeaway. And the second one is that our predictions are calibrated. So when we use traditional methods, the predicted probabilities of having a disease do not match the empirical probabilities. So this happens in traditional methods. But when we use our method, then they match. So we have a method that is more accurate, but also gives probabilities, which are very useful for physicians because then it gives a confidence on how sure the classifier is that this image actually belongs to a person with a problem. So this is like the main takeaway. Now let me go directly into the presentation. I'm going to start talking about a few machine learning basics. Then I'm going to present the probabilistic labels, that is the methodology that we are proposing. And I'm going to talk about what they are, how do we compute them, and what if our computation of these labels is incorrect, what will happen and how to correct it. And finally, I will conclude of why this methodology works and is able to achieve the results that I just talked about. So let me start with the machine learning basics. The general objective of machine learning is to make predictions in previously unseen instances. And to do that, what we usually do is we collect a data set. And in this data set, we have several instances, several examples that we call the feature vector. And we also have the class. In this case, if they have a disease or if they are healthy. Using this historical data, then we input this into a learning algorithm. And this learning algorithm is going to create a classifier. And then we want to use this classifier to make new predictions. Whenever we see a new instance, then we make the prediction, and that's it. That is basically the objective of machine learning. Now, how do we do this traditionally? How would we approach the main task that I presented in this traditional framework? Well, we go and collect images. For example, images of the hip. And then we collect a bunch of images of healthy people, and then we say these images are class 0. And then we do the same for the images with hip dysplasia. We collect a lot of images of people who have actually hip dysplasia, and then we say they are class 1. Then what we do is we input this into a convolutional neural network. That is one of the most common approaches for dealing with images. And then we say, for example, for this image, this belongs to a person with dysplasia. Therefore, the target can be encoded as the probability is 0 of being healthy, and the probability of having dysplasia is 1 because it was diagnosed with dysplasia. So we encode this label with the 0-1 encoding, then we train the model, and then we optimize a loss function. And usually, this loss function is the cross entropy. So the cross entropy has two parts. The first one is the actual label, that in this case is going to be either 0 or 1, depending on the class, and the log of the probability. And this probability is the prediction of the network. So then we want to minimize this loss function. This is what we traditionally do in machine learning. Now, there are some common assumptions for this paradigm to work. And the first one is that we have enough instances in the training set to learn a good classifier. And the second one is that the labels that we get are reliable and objective. And this is usually not the case in medical imaging tasks. So when we want to apply machine learning in medicine, we have usually very few labeled instances for training compared with other image classification tasks where we can have millions of images. For example, if you want to classify a dog versus a cat, you can just go to Google Images and then type cat, and you immediately will get a ton of examples. That is not the case in hip dysplasia or in any medical condition. So usually the number of images that we have available is in the range of a few hundreds at best. And these images, of course, are high dimensional. The second one is that we tend to have subjective labels. And by this, I mean that when I show the same image to different physicians, they might reach to different conclusions. Some of them might say, oh, it is healthy, or I think that they have a problem. So there is not a 100% agreement, which makes the label subjective. The third one is that the calibrated probabilities are important. It is not the same to say, with this image, we have a 53% confidence that they have a disease, than to say we are 100% confident that they have a disease. So this is important for the users to get a sense of how confident is the network in the diagnosis. And the fourth point is that we have lots of background knowledge. The physicians are trained or they train for many years to learn how to interpret these images. So when we build a machine learning model with the traditional methodology, we completely ignore everything that the physicians already know about the problem. But they already know a lot. So maybe if we find a way to incorporate this knowledge into the machine learning task, we might compensate for the lack of data because we can provide extra information to our method. So as I mentioned, the main challenges in using convolutional neural network with images when we have limited data is that one, they tend to overfit, and two, they are not calibrated. And I know that we tend to say that whenever we have a convolutional neural network with a sigmoid function or a softmax function at the end, the outputs can be interpreted as probabilities. But that is not exactly correct in the sense that they are not calibrated. The outputs are numbers in 0 and 1, in the range 0 and 1, and they add up to 1. So they have that in common with probabilities. But they are not proper probabilities in the sense that they do not reflect the likelihood of the data. And I'm going to talk a little bit more about this. But as a short summary, whenever we train a model with the traditional labels, we penalize every time that the network doesn't predict either 0 or 1. So then the network learns how to do this prediction of 0 or 1 most of the time. And this is why they are not calibrated. The network is always very, very confident in the predictions because it is penalized for not being that confident. This is what the loss function is doing. I'm going to go into more details into this. But let me go into the probabilistic labels first, what they are. And it is very, very simple. Instead of using this Y, this target, as a categorical label, so for example, case and control, that can be encoded with the 0-1 encoding. For example, this one, we have an image of a person with dysplasia, and we encode this as a 0-1, representing the class healthy. So it is not healthy, so it is 0, and it has dysplasia, so it is class 1. We are going to replace this traditional label with the probability of X belonging to each of the classes. So for example, the probability of this image being healthy is 0.2, and the probability of having the disease is 0.8. So instead of trying to match the categorical label, we are going to try to match the entire distribution. The good news is that the same approach that we use for training with traditional labels can be applied with probabilistic labels. So we can still optimize the cross entropy, but now instead of making this number 0 or 1, depending on the label, we actually use the probability, 0.2 and 0.8. And then we train the network in the same way. We just change the label. Now, let me give you a simple example of why this makes sense. Let's assume that we want to build a binary classifier that can identify two Gaussians, the orange Gaussian and the blue Gaussian. So this is the data, this is the world. This is what happens in reality. Now, when we want to train the classifier, let's assume that we have very few instances, maybe only 4 of them. So for example, we have 2 examples or 2 instances from the orange distribution and 2 from the blue distribution. So then we build our simple model, a logistic regression model, we build the classifier, and then we find this classification line, this boundary, which works great on the data. But what happens when we apply this to the actual data? Well, it overfits. It does a great job in the training set, but then when we apply this to the test set, then it doesn't do a very good job. And this happens because we didn't have enough training instances. However, what if instead of saying that the labels are orange and blue, we give the actual probabilities? For example, we say that this point is 0.5, 0.5, and maybe this one is 0.7, 0.3. Well, if we do that, then we can learn this model with the probabilistic labels, that if we see it doesn't make a very good job on the training data actually is misclassifying this orange dot. However, since we are giving more information per every instance, then when we apply this into the actual test set, we see that it makes a very good job in finding the optimal boundary. And the reason is that the probabilistic label is saying how close this instance is to the boundary. If the probabilistic label is 0.5, 0.5, then we are saying, oh, this is actually a borderline case. And if this point has the probabilistic label 0.1, 0.9, then we can say, oh, then this one is far away from this boundary. So then this gives extra information to our learning algorithm, and then we can learn a better classifier that generalizes. So, of course, as we increase the number of data, or the number of data available for training, then the categorical or the classifier learned with categorical labels is improving. So it eventually will have the same performance than the probabilistic one. However, look how with maybe 10 instances, a classifier learned with probabilistic labels already reaches the optimal decision boundary, while the categorical needs more than 100. So it needs much more data. And this is the reason why the probabilistic labels are actually very useful. Now, the obvious question is, how do we compute them? Yes, it is a great idea to say, give me the probability distribution, but if I have an image and the only thing that I have available is if the physician said that they have a disease or they are healthy, how do I transform that into a probabilistic label? And this is where we leverage the medical knowledge. So I'm going to give a very general description right now, and then I will go into detail. But the first step is to identify relevant features in the literature. For example, in the case of hip dysplasia, there are two things that the physicians use to make the diagnosis. The first one is this angle alpha between these two bones called the ilium and the acetabulum. And the second one is the ratio of D1 and D2 in the femoral head, that it is this black circle in here. By using these two things, they identify if someone has dysplasia or not. So then we can go to the training set and manually extract these features for each image in the training set. Then we can build a graphical model that relates these features, in this case, the angle and the ratio of D1 and D2, and the categorical label that we have, if they have dysplasia or not. And then we can put a probability distribution in top of these variables. For example, since Y is categorical, well, is binary, we can model this with a Bernoulli distribution with some parameter that says what is the probability of having the disease. And then we can put a distribution on the angle and the coverage, in this case represented by the vector X. And then, for example, I can say that they are Gaussian. And from that, I can estimate the probabilities for every instance in the training set. Now, let me go into more detail into this, and let me guide you step by step on how to do it. Imagine that we have this image, and this image was diagnosed with dysplasia. So then we go and we measure the two quantities that we care about. We measure the angle and we measure the ratio of D1 and D2 that is called the coverage. So let's assume that for this particular image, when we make the manual measurements, we find that the angle is 41 and the coverage is 0.23. So then we create a plot. In this case, we can create a plot because it's a 2D. In general, we can do it with any number of features. And then we put a point in here. This image represents this dot in this plot, where the angle is 41 and the coverage is 0.23. We can repeat the same procedure for all the images that were diagnosed with dysplasia. So then we go through all the images, we measure the angle and the coverage in each of them, and then we create a point in this graph for each of the images. Then we'll repeat the same for every image that was diagnosed as normal. So now we have this plot. And now if you look at this data, they look like a Gaussian might approximate this well enough. So then we can fit a Gaussian to each of the groups. We can fit a Gaussian to the blue group, that is when the person is normal. And then we find the parameters, mu and sigma, the mean and the covariance matrix of this normal distribution. And then we can get this very easily from these points. And we do the same for the orange model. So now we have the model. Now we have the probability of x given y equal healthy, and the probability of x, where x is the pair angle coverage, when y is equal to having dysplasia. Now, then we can use the Bayes theorem to compute the probabilistic label. So for example, if this image was diagnosed with dysplasia, and then I measure that the angle and the coverage is 1 and 23, then I can estimate, then tell me what is the probability of having the dysplasia. And for this, I just use the Bayes theorem. I have this probability of x given y equals 1 that we got from here. So then we can evaluate the PDF and get this number. And then I multiply by the prior. What is the probability of any person having dysplasia? And then just divide by the, by the sum of everything. So then this adds up to 1, the normalization part. And that's it. That is how we compute the probabilistic label using the Bayes theorem. So maybe after doing this computation, we find that the probability of y being equal to 1 is 0.97. Since this is a binary classification problem, then the other one is 0.03. If this was a multi-class problem, well, then we just have to compute this quantity individually for each of the possible classes. But this works exactly the same. And this is how we can get the entire probabilistic label. Then we can go and do this for the entire data set. Oh, something very important about these priors. These priors are the probability of having the dysplasia in the place where you are planning to deploy this algorithm. This is not the probability in your training set. For example, you can have 100 images with dysplasia and 100 images with normal, and then you can say, oh, the probability of being 1 is 0.5. But not really. This probability might be, for example, the incidence of the disease. And then you can get also that from the medical literature, where they say, well, the probability of having dysplasia is 1%, or 1 in every 10,000 cases, or 1 in every 100,000 cases. That is the prior. Not the one in your training set, the one where you want to deploy the algorithm. So now that you have the probabilistic labels, then you can train. You can train the algorithm. Build your convolutional neural network, but now it's this target, and it works. So when we trained with the traditional categorical labels, then we have an accuracy of 74%. And then using exactly the same data and exactly the same starting point in the weights of the convolutional neural network, when we use the probabilistic labels, then we increase the performance from 74 to 80%. So we were very happy about this. And then we decided to try it in a different data set. And then we went with glaucoma. Oh, sorry. One more thing. The probabilities are calibrated. So when we match the predicted probability and the empirical probabilities, we see that in the categorical labels, they do not match. Maybe the network is very confident that this image has dysplasia, and they predict 0.97%, but maybe in the reality, the prediction should have been around 0.50. Maybe it was a borderline case, but the network tends to be very confident. However, in the probabilistic label, then we can see that the predicted and the empirical probabilities actually match. Now we went to glaucoma. So when we repeat the same experiment with glaucoma, we saw a huge improvement from 55 to 69% in performance, again, using the same data We just added this medical knowledge that in this case is the ratio of the cup and the disc in the eye. Every disease has their own way of being diagnosed. So now we have this improvement, and we were very happy. And then we went to fatty liver, and then we were very confused because now the hard labels were giving a performance of 90%, and these probabilistic labels were giving a performance of only 81%. And this is actually where Pune, the contribution of Pune came into place. I was trying to convince her that she was doing something wrong when estimating the probabilistic labels, and this is why it was not working. And in the end, she convinced me that the methodology was wrong and that we had to improve how we train the models with probabilistic labels. So this leads to the third part of the talk. What if the probabilistic labels are incorrect? And this is what happened in the case of fatty liver. It turns out that fatty liver is very hard to diagnose this disease only from an ultrasound image. And that happens because many of the features that the physicians use are very subjective. They are things like, well, they have fatty liver if, so this part here represents the liver, if the liver is brighter than the cortex of the kidney. And that sounds like a good metric, but which part of the liver? This part that is very bright, this part that is very dark, and then we have to compare that with which part of the cortex of the kidney, that is this weird shape in here, with this part that is bright or with this part that is dark? And the answer is we don't know. It is very hard to quantify this. So whenever we extract probabilistic labels using these not very well-defined metrics, the probabilistic labels tend to be incorrect. And when we learn from them, then this happens. The performance goes down. And this is because the probabilistic labels completely ignore the original labels. So for example, imagine that I give you a fixed X, an image, and I have 99 copies of this image. Sorry, 100 copies of this image. And 99 physicians says that this is negative. They don't have the disease. And one physician says that it is positive. But for some reason, so then we have strong reasons to believe that this image is actually healthy. This is negative. But for some reason, when we implement the computation of the probabilistic label, we estimate that the probability of having the disease is 0.7 because we use the wrong features, because we use maybe the data was not Gaussian and the Gaussian is a very bad approximation. For whatever reason, we compute this 0.7. Despite this strong evidence of the categorical labels that this is negative, the current approach that we had was penalizing the network for not predicting 0.7 for that particular image, which is terrible because we are ignoring what the people are actually saying. So this was the main problem. So then we came up with a solution that this is something that we called the regularized probabilistic labels. And then we apply this in 2 steps. The step number 1 is just do what I just told you. Train the model with the probabilistic labels. Use the method that you prefer to extract these probabilities, and then train this network end-to-end, having as an input the image and using this probability as a target, and learn the weights. And then call these weights that you learned theta of P because it was learned with probabilistic labels. And save these weights somewhere in your computer. Then train a second model, but then train this model using the categorical labels. So then basically forget everything that I just said, and then you are going to train a model in the traditional way, where the label is basically one-hot encoding. It's just 0 or 1. Now the trick is the loss function that you are going to use. This loss function will have two parts. The first part is the traditional cross entropy. Just replace this by the label 0 or 1, use the logarithm of the prediction, so this stays the same, but then we are going to regularize. And this is where these weights that we learned from the probabilistic labels come into place. We are going to penalize from deviations from that. So what exactly are we saying in here? And by the way, we are going to weight this by a factor of lambda. This lambda is telling us how much confident we are in our probabilistic labels. Let me put a very simple example. Let's assume that I say, nope, I am very confident that this is how the diagnosis should be made and my probabilistic labels are excellent. So then I make this lambda very, very big. Well, then this model is going to be heavily penalized for learning a set of weights theta when we train with the categorical labels that are far away from the weights that I learned from the probabilistic labels. In theory, if I make this lambda infinite, then the model will try to push this to be 0. So then the weights that I'm going to learn are going to be the same weights than the probabilistic model. And it is going to ignore the categorical labels. And we will have exactly the same thing, the probabilistic labels. The weights of the probabilistic labels. If I make this thing 0, if I make lambda 0, then I'm going to say, forget about whatever you learned with the probabilistic labels. I don't care about those weights. Learn a new set of weights that only use the categorical labels. I don't trust this at all. Whenever you put a lambda somewhere between 0 and infinity, then you have a trade-off. You have a trade-off between using the categorical labels and using the probabilistic labels that you use. And in practice, you can use cross-validation to set a good parameter of lambda. So we have the categorical labels here, we have the predictions here, we have the weights of the probabilistic labels, and we have lambda that controls this. Now, something very, very important. Usually, when we have the cross entropy in here, we have the average cross entropy, which means that we divide this by the number of instances. So this is the average. Look how this 1 over the total number of samples is missing in here. And this was made on purpose. Why? Because as the number of training instances that is represented by m in here increases, then this loss function naturally gives more weight to the categorical labels. So as we accumulate more data, then we start relying more on the categorical labels and less on the probabilistic labels. But when we have few instances, then the probabilistic labels dominate. And when we did this, we got even better results. So this is the orange model. So we went from 74 with the categorical labels to 80 with the probabilistic labels to 83 with this combined or with this trade-off of probabilistic and categorical labels. In the case of glaucoma, we were even happier because then the jump was up to 22% in here. And in the case of fatty liver, this basically corrected the problem of having wrong ways of estimating the probabilities. Yeah, it looks like it is a difference or a loss of 1%, but this is a statistical tie. But now we have the advantage that the regularized labels have basically the same performance as the categorical one, but now they are calibrated. So now they have a much better interpretation as real probabilities. So we consider this a win. So now let me tell you of why we believe that this works. First is because of the performance in the accuracy. For models that are trained with categorical labels, with just categorical labels, these two images are the same. This one and this one. Both of them are class 1. Even when in reality, a physician considers this as a borderline case, they are slightly inclined to say that they might have the disease because of the angle of this bone. And this one, they are completely sure that the person in this image has dysplasia. So there is a real difference, and the physician can identify the difference. But when we train this with categorical labels, we are saying, forget about all of that. Both of them are class 1, and I want you to predict class 1 with 100% confidence. Otherwise, I am going to penalize you. The probabilistic labels don't do that. The probabilistic labels try to force the model to say, no, predict 0.51 in here and predict 1 in this one. So forcing the model to make this real prediction actually restricts the hypothesis space. The weights that can make this prediction 51 and 1, the number of models that can do that is much less than the number of models that can predict 1 for these two images. So then they decrease the chance of overfitting. That is the first one. The second one, what we see here in the y-axis is the probability predicted by the model. And what we see here in the y-axis is the actual probability of that image being healthy or non-healthy. Looked at when we train with categorical labels, most of the predictions of the model are either 0 or 1. And yeah, we have a few points in between here and there, but most of them are in the extremes, which means that the network is always very confident on its prediction. However, when we use the probabilistic label, then the model actually predicts real probabilities. And we can see this alignment here between the prediction and the probabilistic label. Now we are predicting in the entire spectrum, and this is why these things are calibrated. Now we are not penalizing the model for not being confident. We are penalizing the model for not giving the real probability, and this makes a world of difference. Now, this approach that I present here is related to something in machine learning called model distillation. So this is usually a master-student approach, and the master is usually a very complex network that provides the soft labels, and the student is usually a simple model that learns from the master. So basically, they use a very complex neural network to learn the probabilistic labels. Now, these approaches work because, one, this is a very complex model, but second one, because you have tons of data to learn this complex model and to expect that these probabilities are going to be calibrated. You have millions of images, but that is not the case in medical cases. But what we are doing is the inverse procedure in here. The master is a very simple model. It's a very simple graphical model that in this case included two features, the angle and the coverage. But then it involves human intervention because someone needs to go and make this measurement. But the mathematical model itself is very simple. And then we are trying to transmit the knowledge gained by that very simple model that involves a human into a very complex network that doesn't require a human, but that we want to do this automatically. So now we build a complex model that learns from the human and the simple method. So we are basically making the distillation not of a complex model, but of an expert human. Well, this is what I was saying, that the deep networks are usually not calibrated, even if the output is in 0 and 1. And then we can see this by analyzing the loss function that we're using. This is the cross entropy loss function. This is the average cross entropy. M is the number of instances. K is the number of cases. So we multiply the real probability by the log of the predicted probability. And then we want to minimize the negative of this. How do we minimize the cross entropy? For a fixed instance and a fixed class, the prediction that minimizes the cross entropy is this equation in here that it is only saying the proportion of these x's that are of a particular class. In the case of a binary classification task, if I have, well, actually, let me give you a simpler example. With few instances, this estimation might not be accurate, this estimation that we have in here. So imagine a biased coin. I have a coin in here, and this coin has the bias of 0.7. But then we just flip it twice. We have very few training instances. One of them was the heads, and the other one is tails. This equation here says that the optimal prediction that minimizes the cross entropy in this is the proportion of heads and the proportion of tails. So then it will estimate that the probability of heads is 1/2, 0.5. But in reality, it was 0.7. The problem is that we didn't have enough training examples or training instances to make a correct estimation of this. So with enough data, if we were able to make this flipping 1 million times, we will eventually get to the real probability, 0.7. So with enough data, the classifiers that use the sigmoid and the softmax will eventually learn the probabilities from data, in this case, the image and the class directly. The problem is the sampling space. So for example, making the flip 2 times for a coin is not going to be enough. And then we only have 2 options here, head or tails. In the case of images, the sampling space is huge because we work at the pixel level. So usually the pixels can take values between 0 and 255, but then we have the width times the height number of pixels. And then for each of these combinations, we have the possible classes 1 or 0. So with this sampling space, learning the probabilities directly from the data is very, very hard. As an alternative, when we give the probabilistic labels as targets, we are estimating the probabilities using only 2 quantities in the example of hip dysplasia, the angle and the coverage. The sampling space is now just R2 and combined with 0, 1. This sampling space is much lower than the one in the images. But then we can argue that they are equivalent, because this one contains the medical information and how the physician makes the diagnosis. This is still learned from the data, because we have to measure the things, and then we have to estimate the probabilities based on those measurements. So we are still learning the probabilities from the data, but these probabilities are much easier to estimate than trying to do it directly from the images. So just to conclude, the probabilistic labels increase the performance of model when we train models with very few instances, and we were able to see gains of up to 20% in accuracy. The predictions of this model with regularized probabilistic labels are better calibrated, which is very relevant for the medical tasks. The third option is that the trick of doing regularization really helps whenever we have misleading probabilistic labels. And this decreases the risk of using the probabilistic labels, because then you can say, well, what if they are wrong? Well, if they are wrong, if you do the cross-validation properly, the algorithm will figure out that it cannot trust the probabilities and will assign a very low value of lambda. So the model itself will use them if they are appropriate, and it will ignore them if they are not. And we expect this general framework to be helpful not only in these 3 particular tasks, but in any task where the expert knowledge can be encoded as probabilities. And yeah, basically, I am happy to take questions if there is any. And yeah, thanks to everyone who was involved. That you see in here in the logos are many people, the university, Amii, this one is from Mexico, and the company Meadow AI, who is the one who provided the datasets. So yeah, that's all on my side. I am happy to take questions.
So maybe I'll go first. Great talk. Lots of good stuff.
Thank you.
Now, you used internal cross-validation to find the value of lambda for those different tasks. Did you look at those values of lambda? Did they confirm that, in fact, the first and third tasks, that lambda was just very small because you want to ignore the ones, and it was very large for the middle one, or did you actually look at those lambdas?
Yes, I don't remember the exact value, but yes, we look at the lambda, and yes, in the case of fatty liver, basically it was ignoring the probabilistic labels for the prediction, but not for the calibration. So, I mean, it was around 50, the value. It was not too high, it was not too low. So it used the values to improve the calibration, but then it ignored them for the actual prediction. So the answer is yes. We look at them and they confirm what we were thinking.
As a follow-up, would that give advice to medical people to say, maybe that the ways you're trying to evaluate fatty liver is wrong, or it's misleading, or at least needs to be taught better or something?
Maybe. I mean, yes. The short answer is yes, that this reflects that in many medical problems, the way of making the diagnosis is not very well defined, and it is very hard to reproduce, because there is also the possibility that they have their heuristics, and then the problem is that we don't know how to code them. For example, in this problem of fatty liver, they want to check if the liver, that is this big structure in here, is brighter than the boundary of this other small structure in here. So when we tried to code it, we had no idea how to do it because we didn't know what to compare. Maybe the experts say, oh, it is obvious, you have to compare this part and this part in this particular image. And maybe for them it's easier. Now, to be honest, there is a lot of disagreement. We made a few experiments with this, and then we give the same image in 2 different days to the same person, to the same expert, that they know what they are doing, they are very good. But in 2 different days, they gave different responses. Same expert, same image, just they look at different things in different days. So then this also talks about...
What was this looking at the overall assessment of fatty liver or not, or looking at that specific sub-question of what part, how does the brightness compare?
No, it was the specific question of fatty liver or not.
Okay.
Yeah.
Cool. I see. Carrick has a question.
Yes, just to confirm, the features used to compute the probabilistic labels are measured by hand. For example, the angle used in the graphical model for hip dysplasia was measured by a human. Yes, those are measured by hand. Yeah, so it involves extra work of the people. Now, we believe that it is a good payoff because you see an increase in the performance. And the second one is you only have to do that during training. Once that the network learns the mapping directly from the images to the to the prediction, then for using the network, you don't have to manually measure the angles anymore. This is only for the training stage. And in the training stage, you have very limited images by definition, just a few hundred. For example, in hip dysplasia, you had 400 images. For fatty liver, you had around 200. And for glaucoma, we had around 100. So yes, you have to do it manually. It takes around 1 day of work. But once that you do that, then the rest is done automatically. And most importantly, when you make the prediction, you don't need a human at all for this one.
I think Roxanne had a hand up, or is that just...
I don't know. I see a second question in the chat. Oh, sorry. Yeah, go ahead.
Oh, sorry. Yeah. No, that was a really good talk, Roberto. Thank you. And
Thank you.
I was really interested in the part about the regularization. So where you had the base probability that you were using with the Bayes rule. That's really interesting. And I was thinking, is there a way to like adapt that probability? Because you can imagine that probability changing over time, right? Like if people start referring more patients for this kind of testing or less patients or something changes in the pipeline, then you imagine that the base probability of the condition will change. Yeah.
Yes, that is correct. That is correct. What do I have this? The base rule here. You are completely right. These probabilities or these priors can change over time or over space as well. For example, hip dysplasia is more common in Africa than in North America. So the prior is different here and there. So we have two options in there. One is we create the probabilistic labels for Africa and then we train the model, and then for North America and then we train the model. That is one. The second alternative that we can use is instead of learning this probability of y equal to 1 given x, we can make the model to learn this thing in here, the probability of x given that y is equal to 1. So for example, maybe in here, instead of having this as the target, this target here is the probability of y equal to 1 given x. Then we can train two models. One model that computes the probability of x given y, and the second one, y equal to 1, and the second one that computes the y equal to 0. So then instead of learning this as a whole, then we train models with this probability in here, with the conditional of x given y. And then we can just adapt this by multiplying this externally. So we run the network. We run the network for y equal to 1. We run the network for y equal to 0, and then we get this. And then we externally multiply by the priors and make the normalization. And that could be a second option. Both of them imply training more than one model, but that's how we can use it.
Yeah, that sounds really awesome. Thank you.
Yeah. Now thank you. I have a question here in the chat. What do you see as the implications for probabilistic labeling beyond the medical context? Will it be useful in other domains? I think so. I haven't tried it, but I think so. For example, where can we, or where can I see a direct application of this? Maybe in fault diagnosis in machinery. So sometimes you want to predict when you need to give maintenance to an industrial machine, or when some part is going to break. And many people do that based on manually inspecting the machine or on taking pictures. So I believe that it can have a direct application in there. I haven't given it a lot of thought in where else can we use it, but in general, wherever we can express whenever we can encode how the humans do it in a probabilistic way, I believe that we can use the probabilistic labels. But yeah, I am working mostly with medical images, so it's hard for me to give a very concrete example right now.
Hi, Roberto. It's Al Murtha. I'm a clinician, and so I'm acutely aware of how the failures of clinicians in terms of we're used as the gold standard for these types of training systems, but we know that we're not always right, and so and that causes problems when a computer is trying to emulate what we do. Yeah. And as a computing scientist, I know that the goal is to get the computer to do as well or better than the human. But what about feeding back the other way? Like when you have a scenario where, let's say, the true gold standard is revealed with time. So clinicians are always tasked with make a prediction with the current information, and hopefully most of the time that's right, but sometimes it's wrong. But with the benefit of time, the true gold standard gets revealed. So if we divide the data into one time point, a second time point, is there a way that we can figure out, or the computer can uncover, what clinicians are doing wrong? So find the ones where we make the bad predictions and then analyze those ones to find out which features are clinicians getting tripped up on. because that's traditionally that's how medicine evolved before machine learning, became involved, is we would do things one way, and eventually someone would discover that, oh, that feature that we're looking at is actually not predictive, or it's a false feature. And so it's a slower process because it takes a human's own personal experience to see that. But is there a
Yes.
way that you could feed back to the clinicians and say, stop looking at that feature? It actually causes you to be wrong more than right.
I mean, that is a good question. And ideally, computers should be able to do that. But I say that ideally, because, for example, if we want the computer to learn everything directly from the data, then we need tons of data. And the problem is that we don't have it. So for example, if we have this evolution over time of 10 or 100 or 1,000 patients, I mean, we can try to use that, definitely. And having it is better than not having it. But it will be very hard for the computer to learn by itself everything with only 1,000 instances. Or this is what I believe. The other option is to use simpler models. But those simpler models require the manual computation of features, which is what we don't know in the first place. So yeah, I mean, that is a very interesting question. I don't know how to do it, but that would be ideal, to make the computer help us understand more about the process itself. That will be great. In my opinion, most of the current algorithms are not designed to do that, because I believe that implies to create algorithms that learn the cause and effect. And that is a harder problem. Most of the machine learning are based on correlations, not on causation. So yes, the answer is yes, that would be great. I'm not sure how to do it, but it is something that many people are exploring, including ourselves. We are trying to bring some light into that.
And just to follow, like in my simplistic view of it, it basically, you would look in the future, so to speak, at time point 2, and say, segregate the data into 2 sets. One's where the clinicians did poorly on, and one's where they did well on, and analyze to see what are the different features between those 2 subsets. And then you could inform clinicians that, 7 of the 10 things you look at are useful. Those other 3 keep tripping you up, so stop using them.
Yeah, definitely. We can try experiments on this kind of things. Absolutely.
Because the problem always is that the clinician gold standard has a known, false prediction, right? And so if we can improve the prediction, well, then that can feed back again to the algorithm if clinicians are giving a better gold standard to be compared to. So
no, I agree. I agree. Yeah, definitely.
Thank you.
Great question. Thanks, Al. I think I see that Kelly has her hand up, and maybe that'll be the last question because it is after 1 o'clock. So Kelly?
Sorry, just to build onto the clinical practice, I was just wondering if you were going to implement your model tomorrow into real life clinical practice, would you change anything about it?
Oh, well, so there are 2 different things that we have to do. One is like the research question itself, the computational questions of how do we learn better with few instances, and that is mostly an academic question. The second one is how do we deploy these things, and for example, this is where companies like Meadow come into place, where they take the research and then they try to make the implementation on the real life. If I were to deploy this in a clinic, I may do it in a different way. I will still use things like probabilistic labels, but I am aware that this modeling here is still a black box from the point of view of the clinician, where you give an image as an input, and then the output is a probability. Yes, that gives more information than saying healthy or non-healthy. It tells you 75% of probability of being healthy. Still, I believe that for a practitioner, that is not going to be enough. They want to know how you came up with that conclusion. So if I were going to deploy something like this in clinical practice, I will try to provide more feedback to the users. For example, we know that the clinicians in this case care about the alpha and care about the coverage. So instead of creating a black box, I will create an algorithm that starts by making a segmentation of the ilium and the acetabulum. And then I will show exactly what is the angle that I am computing. And then I will do the same for these 3 points in here and the ratio D1 and D2. And I will show these 2 points in the original image. And then I will say, based on these landmarks, I compute an alpha of 41 and then a coverage of 0.23. And then using this graphical model, then I estimate that the probability of having the disease is this one, because this is what the data is indicating. So then I will guide the clinician step by step on how I am doing this. And this is in fact how we translated this into one of the products that Meadow is using. So instead of having a black box that makes a final prediction that no one can explain, we built something that we call Debuggable AI. I don't claim that the algorithm is explainable, because the algorithm that would make the segmentation is still a black box. However, when you compare the segmentation mask that the algorithm creates with the actual image, then you can say the algorithm is wrong or the algorithm is right very quickly. So you can debug, and then you can say, I will not trust the machine learning algorithm because the segmentation doesn't make sense. Therefore, the prediction doesn't make sense. Or you can say, yeah, this is how I will have segmented this. So then I have more reasons to believe in the algorithm, because they are measuring the angle, they are measuring this thing, and based on that, they are reaching that conclusion. So this work that I am presenting here was more into the academic part. How do we learn more effectively? But for the clinical part, I will take a slightly different approach during the implementation. And this is in fact what Meadow is doing, because the clinicians want to know the rationale of the decision.
Yeah, that's a great answer. So before we get into any deep learning into our clinical practice, we're going to have our simple models that we can explain to guide, essentially.
Well, actually, the algorithm that creates the segmentation is a very complex deep learning algorithm. Mm-hmm. So we are still using, actually, we are using exactly the same networks that we are using in here, and the complexity is the same. The difference is that now you can very easily verify what the network is doing, because you can create a mask, you can visualize it. So then that allows you to say, okay, this is what the network is doing. Once the deep learning is used, then the rest is a very simple algorithm. But solving the segmentation task is a very complex thing in itself, with the advantage that we receive direct feedback on what the network predicted.
Yeah, that makes sense. Thank you.
Yep. Oh, thank you. Really interesting work, Roberto. Oh, thanks a lot, Carrick. Thanks a lot. I appreciate it. Yeah, thanks. Very interesting. Okay, thanks, John. Thanks a lot. So, any other question that people have? Okay, so what do we do now? Do I just close the call, or?
If you do not have any questions, thanks, Roberto, for a wonderful talk and engaging discussions. We'll meet next week for another AI seminar. Till then, stay safe, stay healthy. Bye-bye, everyone.
Okay, perfect. Thanks a lot.
Thanks, Roberto.
Bye.